What's up guys, we continue to learn dynamic programming. This is the fourth video of the course, Dynamic Programming for Beginners. And today we are going to solve a few more problems and outline the basic steps required for a dynamic programming solution. I apologize for not publishing the video on Sunday. I had to deal with some personal stuff, but I'll try to stick to a schedule as much as I can. Anyways, let's quickly recap what we've learned from previous lecture. So in the previous lecture, we touched the tip of the iceberg by solving an elementary problem in which we had to find the sum of all the numbers from 1 to n. The problem was so simple that in reality we didn't even need dynamic programming, but we used it anyway just for the sake of example. So say n equals to 5. We had to find the sum of all the numbers like 1 plus 2 plus 3 plus 4 plus 5, right? For n equals 5. So we first solved the problem when n equals to 1. Then we solved the problem when n equals to 2. Then, knowing the result of 2, we solved the problem when n equals to 3. And at some point in time, we were able to devise the general formula which would solve the problem for any given n. So the formula was f of n equals f of n minus 1 plus n, right? We also implemented the solution in Go, in which we created an array of size n plus 1 and used it as a cache to access the result of a previous subproblem. So for n equals 5, we would have an array of size 6, right? So let's create an array of 6 elements. 5, right? So in here, for instance, when n equals to 0, the sum is 0. When n equals to 1, the sum of all the elements is just the element itself, so it's 1. So for 2, it's 3. Then for 3 elements, it's 6. 6. For 4 elements, it's 10. And then for 5 elements, when n equals to 5, the answer is 15. So the result is in the last element. And when we solve problems with dynamic programming, we learn that we don't want to recalculate things. We want to rely on existing solutions, on the information that we already know, right? This is the core idea. In this example, n equals to 5. But now if I ask you what is the sum of all the numbers when n equals to 6, you can immediately tell me that the answer is 21, right? So if this is 6, then plus 6, the answer is 21. Why? Because all you have to do is just add 6 to 15, right? To this 15 number. And that's it. You don't have to recalculate everything from the beginning. You already know that when n equals to 5, the result is 15. So when n equals to 6, it's just plus 6, so 21. So we just add 6 to 15. This technique is called memoization. Memoization. We cache the result of a computation so that we can reuse it later, meaning that we optimize the time complexity by giving up space. It's a time-memory trade-off. Okay, so you already know a lot about dynamic programming, and it's time to review a little bit more real problem, which is called a climbing stairs problem. This is a popular problem that you may be asked during the phone screen interview at such companies as Google, Amazon, Facebook, and so on. The reason why I say phone screen interview is because the problem is very simple, and phone screen interviews are generally simpler than on-site interviews. Okay, so there are many different variations of the problem, and one of them is that there is a staircase and your goal is to answer the question, in how many distinct ways can you climb to the top, right? So let's clear the board. So we are given a staircase of size n, and there is a constraint. You can either climb 1 or 2 steps at a time, right? So I decided to visualize this problem because I felt like the description in the video that I gave was not clear enough. So we need to find the total number of ways to get to the top of the staircase, and in this case we have 4 stairs. So let's look at the first way. Basically, we just make 4 small steps, 1 step at a time, right? So this is the first way. The second way would be small step, then 1 jump, and another small step. So this is the second way. The third way to get to the top is by making 2 steps first, then 1 step and 1 step. This is the third. The fourth one is 1 step first, then 1 more step, and 2 steps at a time. And then the last one is we basically make 2 big jumps. So in total, we have 5 different ways to get to the top of the staircase. So how do we solve this problem? Well, the first thing we need to do is to express our goal as an objective function. What is an objective function? The objective function is the function that you want to minimize or maximize in your problem. For instance, if we had to find the cost of something, most likely we would want to minimize cost. If this were a profit, we would potentially want to maximize profit. In our case, the objective function is the distinct number of ways to reach to a certain stair. In a way, it's a minimization problem. So let's define f of I as the number of steps to the ith stair. So we will say f of I is, so we basically just want to write down the description. F of I is the number of steps, is the number of steps to the ith stair. It's always a good idea to write your objective function down along with its description. It will help you to solve the problem faster. Also, defining the objective function is almost 50% of the solution. The definition of the objective function is usually in the problem description itself. You will soon learn to write objective functions on your own. Great. So we have the objective function, right? And now the second step is to break the problem down into simpler sub-problems and identify the base cases. Remember, dynamic programming is always about breaking down the problem into simpler sub-problems, into smaller sub-problems. And we need base cases to identify boundaries of the problem. How do we do that? What I usually do is solve the problem for such input values that a computer is not even needed. Let's solve this problem for when we only have 2 staircases. Let's do it here. Let me clear this and I'll do it from scratch. So let's say this is our staircase, and that's good enough. And we want to solve the problem when we only have 2 stairs, right? So how do we get to how many distinct ways to get to the second stair? So let's calculate them. So this is the first stair, this is the second stair. And we are only allowed to make either 1 or 2 steps at a time, right? So this is the first way, and this is the second way. That's it. There is no other way to get to the second stair. So we'll say f of 2 equals to 2. We don't need a computer to calculate that, right? So now let's calculate f of 1. How many ways to get to the first stair? It's just one way, right? There is no other way to get to the first stair. It's just one. So we'll say f of 1 equals to 1. So notice here that when we solve these small problems, we can always sort of like refer to the objective function, where we say f of I is the number of steps to the ith stair. So in this case, 2 is the ith stair, which is the stair we are interested in. Now, is this the smallest possible subproblem that we can solve? No, there is even smaller one, as usual. So the smallest subproblem here is when we don't have a staircase at all. So it's basically f of 0, right? It's basically we're on the ground, we're here. So how many steps, how many distinct ways there to reach the top of the staircase that does not exist? It's just one, right? We do nothing. It's just one way to get, it's just one distinct way to get there. It's just doing nothing. It also counts as a way to get to the top. Okay, so we have our base cases, the induction basis, right? And now the third step is to write down the recurrence relation for the optimized objective function. So how do we determine the recurrence relation? Sometimes you can spot the pattern by solving the problem for a few more input values, right? So if we would solve the problem for f3, f4, and then maybe f5, we would notice that there is a certain pattern, and we would be able to devise the formula for any given n. Sometimes it's hard and you have to think. So let's see how can we do it in this problem. Let's say we're at the top, at the top of the staircase. From where could we get here? We know that we're allowed to make either 1 or 2 steps at a time only, right? So it means that we could get here either from the second stair, or from the first stair. So this is n minus 1 and this is n minus 2, right? And that is it. We can't get there from anywhere else. So how do we know the total number of ways? Well, we need to add these two guys together, right? As simple as that. The equation would become f of n equals f of n minus 1 plus f of n minus 2, right? In combinatorics, this is called the rule of sum or addition principle. It's a basic counting principle. Feel free to read about it, but the idea is that if we have ways to do something and B ways of doing something else, and we cannot do both of those things at the same time, then there are A plus B ways to choose one of the actions. In our case, we always choose either to make 1 step or 2 steps, which is why we can apply the rule of sum. We have 2 disjoint sets, and we apply the union operation here. It all comes down from the set theory. Okay, so we have the recurrence relation. And the last 2 things I would like to mention today is the 4th and 5th steps needed for a dynamic programming solution. Let's clear the board and write those things down. Okay, so the first step that we want to take when we write a solution, when we solve a dynamic programming problem, is when we need to define objective function. So let's write it down. Define objective function. Second. Now, the second step is identifying the base cases. So let's write it down as well. Identify base cases. So these are the boundaries of your problem, the starting points of the dynamic programming algorithm. Now, the third step would be recurrence relation. Recurrence relation. Recurrence relation is basically the transition function. It's the function that allows you to transition from one subproblem to the other subproblem. Okay, and then the fourth one is order of computation. Order of computation. Order of computation. So it means we need to determine the order in which subproblems are solved. In our case, we rely on, for the problem that we were just solving, we were relying on n-1 and n-2. So we have a certain order here. We need to calculate smaller n values first. Sometimes the order is different, and we'll review such problems in our future videos. Okay, and then the last step is location of the answer. Location of the answer. This basically means where we are looking for the answer. So in our case, the answer is in f of n, right? Sometimes the answer to the problem can reside in f of 0. So we're going to look at the implementation and you will understand why it's f of n. Okay, so this is your framework. These are the general steps that you can follow in order to solve pretty much any dynamic programming problem. We are going to use this framework as we review other problems. Meanwhile, let's implement the solution for the climbing stairs problem. All right, so we have this climbing stairs problem, right? So let's read the description. You're climbing a staircase. It takes n steps to reach to the top. Each time you can either climb 1 or 2 steps. In how many distinct ways can you climb to the top? Great. So I've got this framework for solving dynamic programming problems. We have 5 steps. So let's go over each step before we dive into the solution. So define the objective function. This is the first step you should always take when you solve dynamic programming problems. And as we mentioned before, in order to define the objective function, you should read the description carefully. So we've already done that, right? So we know that f of I is the number of distinct ways to reach the ith stair, right? So we basically just look at the description, and many times you will be able to do it easily. Sometimes it's a little bit more complicated because you may have a few more states, a few more variables. So in certain cases, your objective function may be something like ij or ijk, you know. So it depends on the problem. We'll review more problems in our future videos, and we'll have a slightly more complicated objective functions. So you will be able to sort of like grasp the idea. Awesome. Okay, so now let's move on to identify base cases. Identify base cases. So we already know our base cases. When we're at the ground, f of 0 equals to 1, meaning that you don't have to do anything in order to reach the top. And doing nothing is just 1. Sort of like it also counts. Now, when we want to reach the first stair, when n equals to 1, there is only one way to get there. It's just make one step. And that should be good enough, right? We could continue doing like f of 2 and so on, but we already know that our recurrence relation function is f of n, so f of n minus 1 plus f of n minus 2. So we only need two base cases here, f of 0 and f of 1. Awesome. So what's the order of execution? So the order of execution is bottom up. The reason why is because we always rely on the values from the two previous subproblems. Sometimes the order of execution is slightly different because your recurrence relation function may be, looking something like f of n plus 1 equals f of, I don't know, n plus whatever 1, let's say. So something like that. So in this case, you're kind of like indirectly trying to set future values, future results based on the information that you already have. In our case, it's bottom up since we always rely on the values from the previous subproblems. Okay, and then the last thing is where to look for the answer. So the answer is going to be in f of n, and I'm going to show you why. So now we have all the information needed in order to implement the algorithm, in order to implement the climb stairs function. So let's do it. So the first thing I want to do here is to allocate memory for our subproblems. And it's going to be an array of integers of the size n plus 1. So we'll set our base cases. The dp of 0 is 1, sorry. dp of 1 is 1. You see, like, basically now we have all this information here, and we can just apply or like translate it in code. That's all we have to do. Now we can run the loop from 2 to the n, and for each subproblem, we just need to apply our transition function, our recurrence relation, which is f of n minus 1, I minus 1 plus dp of I minus 2. And that's pretty much it. Now, where is the answer to the problem? As we've said, it's the last element in our cache. So return dp of n. Awesome. So now let's try to test this. I'm going to generate a test for this file, and I'm going to do two tests really here. So simple test 1 with arguments such as n equals to 3. We want 3 back, and then when n equals to 5, we should get 8 distinct ways to get to the top. Let's give it a try. Awesome. So all the tests passed, meaning that our function worked as expected. Now let's quickly do the time complexity and space complexity analysis here. So what is the time complexity of this function? So the time complexity here is O of n, right? The reason why is because we need to go over all the stairs. And then space complexity is also O of n because we allocate an array of size n plus 1. So, and maybe you can think about like a way to optimize this function in terms of space. So if you have any ideas, please post it in your comments and we'll review it together. Thank you so much, and I'll see you next Sunday. Take care, guys, and enjoy the rest of your day. Bye.